Hi, I'm Professor Goins. In this video, I want to take a look at finding the derivative of an inverse function. Meaning, if I know how to differentiate a function which has an inverse, can I use the derivative of that original function to help me find the derivative of its inverse? All right, let's start by taking a look at a property of inverse functions. If I take the composition of a function with its inverse, what happens is those two operations cancel. The consecutive operation of a function followed by its inverse in either order will again have the net effect of canceling the operations, meaning that the simplification of this would be just the original input. All right, well, what I'm going to do is I'm going to think of this then as an equation, and I'm going to differentiate it. So if I differentiate both sides of this, on the left-hand side, this is the derivative of a composition, which is the chain rule. And the chain rule says to take the derivative of the outside function first, so that would give you f prime evaluated at f inverse. And then the chain rule says take the function on the inside and bring out a factor of its derivative, meaning I would have f inverse prime of x. So this right here, this notation is the derivative of the inverse of f. And then on the other side, I've got the derivative of x, which of course is 1. Then what I can do is I can solve this equation for the derivative of the inverse. If I divide both sides by this factor, that would give me f inverse, the derivative of that would be the reciprocal of f prime evaluated at f inverse. And this right here is the formula that we will work with. So notice on the, I want to find the derivative of an inverse, what do I need to know? Well, I need to know the inverse function, and then I need to know the derivative of the original function. I take the composition of those, take the reciprocal, and that gives me the derivative of the inverse. All right, what I'm going to do is I'm going to take a look at 3 examples, so 3 different types of functions, and use this formula to find the derivatives. Okay, first example, so let me say it this way. Find the first derivatives. And I'm going to pick 3 types of functions. First and foremost, let's pick a function that we really don't need to use this, but it's going to kind of show me how the formula works, how we piece it together, and that will give us more confidence with the remaining examples. So we'll see how the functions all fit together. Let's start with the the cube root function. So f of x is x to the 1/3, or the cube root. Part B, let's do a different category of functions. Let's do a natural log. And then for part C, let's do the inverse sine function. So 3 different types of functions here. Okay, so here we go, solution. If I want to find the derivative of this, so let's write this out for part A. I'm trying to find, here I'm going to go back and forth between prime notation or Leibniz's notation, but if I'm trying to find the derivative of the cube root, let's match this up with the formula in that red box. So this is the derivative of the cube root, this is the function, the f inverse, so therefore, we've got the derivative of f inverse. What that means is I'm going to identify f inverse is the cube root. which tells me that the original function f would be the inverse of the cube root, which is x cubed. So these are inverses of each other. All right, looking at that box, what do we need to find the derivative of the inverse function? I have to take the reciprocal of f prime evaluated at f inverse. Well, f prime, this is just going to be a power rule. So this is f prime is gives me 3x squared. All right. Using that formula in the box then, this is 1 over f prime evaluated at f inverse, which means I take the inverse function and I plug that into the derivative. So f prime evaluated at f inverse. This gives me 1 over cube root gets plugged into 3x squared, so that would be 3 times the cube root of x squared. And then let's simplify that. The cube root is the 1/3 power, so that is x to the 1/3 squared. Power to a power, we multiply. That would give me 1 over 3x to the 2/3. And certainly we can check by using the power rule. So this, again, this is the answer. This is the derivative of the cube root. But as a quick check, if I take the derivative of the cube root using the power rule, again, remember what we have to do when I differentiate any function that has a radical is I'll turn this into a rational exponent, giving me the derivative of x to the 1/3, for which we use the power rule, meaning the exponent comes down, I decrease the exponent by 1, and then I can make that an exponent positive by flipping it to the denominator, so that would be 1 over 3x to the 2/3, and of course it matches what I have in green there. Okay, so this tells me, again, this provides the format for how I work with this formula. I have to find the, if I know this is the inverse, I have to identify the original function, or in other words, the inverse of that, and then I also have to identify the derivative of that function f, and then I take the reciprocal of their composition. Okay, so let's do the same thing with the natural log, and then followed by the sine inverse. B. All right, we are looking for the derivative of the natural log, so therefore I need to identify what are the functions. What's f inverse, what's f, what's the derivative of f. All right, let's do this down below here. What I'm taking the derivative of is the inverse function. Therefore, the inverse function is the natural log. What was the original function then? Well, the inverse of the natural log, remember natural log is log base e. So just as a reminder, this is log base e. That's the only logarithm that has a different notation. And then the inverse of log base e would be the exponential function base e. This is everybody's favorite derivative because the derivative is itself. F prime is also e to the x. Okay, so now I have everything in place. And just like over here, the derivative is the reciprocal of f prime evaluated at f inverse. That gives me 1 over, so again, f prime is what I'm plugging the inverse into. So I take f inverse, which is the natural log, I plug that into f prime, giving me e to the natural log of x. Now here, this is the composition of the function with its inverse. the composition of a function with its inverse has the net effect of doing nothing to the input, meaning that this simplifies to just x, giving me the final result that the derivative of the natural log is 1 over x. Finally, for part C, I've got the derivative of sine inverse. Let's identify the functions here. F inverse is sine inverse. So then, of course, the original function f would be the sine function. The derivative of the sine function is the cosine function. So this is f prime of x equals cosine. I have the three functions that I need, and now I plug things into the formula. This gives me 1 over, one more time, it's the derivative with the inverse plugged into that. This is the derivative, this is the inverse. I'm going to take this and plug it into cosine. That gives me the reciprocal of cosine evaluated at sine inverse. Now this is the derivative of sine inverse. However, it's not particularly useful in computational situations. So what we do is I'm going to rewrite that function so that it's in a more user-friendly format. All right, here's how I do that. So let's do this down below. I'm gonna take a look at the expression cosine of sine inverse. Now the input for a cosine function is an angle. Equivalently, the output for a sine inverse is an angle. So what I'm going to do is I'm going to do a change of variables, and I'm going to say theta is equal to sine inverse, meaning what I'm ultimately trying to find is cosine of theta. Right, because this is theta, so I'm trying to find cosine of theta. So I just relabeled what is the argument of the cosine as the variable theta. Okay, how do I then find the cosine of theta if I have this equation? Well, I'm going to take the sine of both sides, and that would give me sine of theta is equal to x. What I have now is I know that the sine of theta is x. I want to find the cosine of theta. And there's a couple traditional ways that you could do that. You could either use what's called a reference angle, or you could use a trig identity. In this case, the trig identity, of course, that relates the sine and the cosine is the Pythagorean identity. So we could use that. I am going to use the reference triangle simply because it's more, well, I shouldn't say it's more useful. Both of them are useful, but that's the way that I'll do it. If you want to see using a trig identity, let me know in the comments and I can add another video where I show that as well. But let's go through and use a reference triangle. I think that's what students usually prefer. Okay. What I'm going to do is I'm going to use this information right here, the sine of theta equals x, and I'm going to build a triangle out of that. The right triangle definition of the sine is it's the opposite over the hypotenuse. Therefore, I'm going to rewrite x as x over 1, so I have it as a ratio. That would give me, with respect to this angle theta, the opposite side would be over here, so this would be an x. The hypotenuse would be a 1, and then the adjacent side is the unknown. To solve for the adjacent side, this is a right triangle. Therefore, the Pythagorean identity applies, or I'm sorry, the Pythagorean theorem. Therefore, this gives me the square of the hypotenuse is the sum of the squares of the two legs. And a is what I'm trying to find, so I want to write a in terms of x. I'll subtract x squared, giving me 1 minus x squared is a squared. I'll take the square root, a giving me the square root of 1 minus x squared. And I'll use the positive radical since I'm thinking of this as a length. So therefore that gives me the positive square root of 1 minus x squared. Now I have this reference triangle completed, and now let's go back to the beginning of what we were ultimately trying to find. At the very beginning, I wanted to find, again, let me section this off. We were trying to find the derivative of the sine inverse function. What we found is it's the reciprocal of 1 over cosine of sine inverse. Through this work over here, we rewrote cosine of sine inverse as the cosine of theta. This would give you the reciprocal of cosine of theta. And the cosine of theta, well, I have a triangle where I can find cosine of theta. Cosine is the adjacent over the hypotenuse. Therefore, this would give you the square root of 1 minus x squared over 1. And of course, this denominator here we can leave off. That would give me a final answer of the reciprocal of the square root of 1 minus x squared. And this right here is the derivative of the sine inverse function. We could do a similar procedure with all the other inverse trig functions and just follow along with that same format. Okay, so